I'd like to start by thanking Deb and Dennis and the other organisers, and particularly also Joan Garfield for her role in making this visit possible. It's really great to be here. I mean, who wouldn't want to be here? I mean, it's not winter, it's summer, it's Ozpots, it's wonderful meeting, wonderful people. Summer, I'm here a bit early, I hear, for the football, but I quite like the hotel, so I wouldn't mind hanging around. But, it's all wonderful here. And, of course, going a little bit for this is your world. You're down there at the yellow dot somewhere. Here's mine. It gets lonely down there. Okay, now the recession's been biting a bit down in New Zealand, so I thought I should do my part for my sort of country and my city and show up a few tourist shots. So please come down and save our economy. Well, Deb already told you a little bit about where I come from. That's Auckland Stats Department. It's one of those buildings where it's better to be inside looking out, if you know what I mean. 32 statisticians. She's done all this, so we'll go over it quickly. Now, she'd also introduced you to a little bit about New Zealand, but I thought I'd fill in a few more details. New Zealand is populated by misty-eyed romantics. There's a few of them here. This is the national rugby team doing a misty-eyed romantic war dance, which they do before matches. We're also famous for the poetry of our place names. And only the geographically really aware will know that there's also a third island to New Zealand. West Island. I joke, why don't you? I was going to say it's way off to the west. It is called West Island. And that's what it looks like. Now, we don't talk about it much. It's all desert in the centre. Hardly anybody lives there. Now, if there are any Australians here, they'd be getting a bit upset by now. They'd be saying, the Australian's way bigger than that. I've played ducks and drakes with the geography. And yes, I have rescaled it a little. I applied in a relative importance metric. Okay, where am I going next? Now, like all educational experiences, this talk has a pretest, and it's about inference and so on, so I just want first you to just quickly eyeball that and tell me, are those two groups different? Who thinks they're different? Who thinks they're the same? Who doesn't know? Who won't say? Sounds a bit like any ordinary class, doesn't it? Luckily, this is just a practice test. And the post-test, if you fail, it invalidates your dinner ticket for tonight. Who automatically interpret that question inferentially? That's the real question on this sheet. Who did interpret it descriptively? Okay, I'm surprised, actually. I thought everybody would go for it inferentially. Actually, there's another thing. What is the single correct answer to every question in statistics? You didn't know that. Well, this is the guy who put me onto this. This is a friend of mine in Waterloo in Canada. His name is Jock Mackay, really bright guy. And here's the answer. Okay. So if we're going to interpret the question above descriptively, then obviously those things are different. Let me count the ways. If we are going to interpret inferentially, well, then it was a trick question because there's not enough information on that display to tell. Okay. You have to read it. You need things like sample size to be able to make sense of that question, and that's sort of confusing, I guess. Okay, so let's go now to the talk. We'll sort of go to the talk. These are my partners in crime in this work. Maxine Fancook from Auckland, Matt Regan, who is here, and Nick Horton from Smith College, who is also here, And Nick is just the winner of the 2009 Waller Award, so way to go, Nick. Somebody else who's here has got nothing to do with this talk, but he does have something to do with George's brilliant talk from this morning, because that's Wayne Stewart, who is here with the Reverend Thomas Bayes. And the Reverend Thomas Bayes engages in animated debate with Freaky Frequentist. So no sort of prizes for guessing who gets given all the best lines. Now, the background to the work that we'll be talking about here is things we've been doing in New Zealand, actually things we've been doing in New Zealand in K-12, but don't let that put you off. Some of it will still be relevant. I hope all of it will still be relevant. Recently, a couple of years ago, a door opened momentarily, just a crack. The planets were all lined up. And there was a new curriculum to be written. Our relationships were right with all those groups that are listed there, including the mathematicians who knew to butt out. And so we had an opportunity, one chance, take it and run with it, or wait another 18 years, which is how long the last curriculum lasted. So the group of us decided, yeah, we'll take a risk, we'll take it and run with it, and we managed to slip through the cracks of modern new curriculum. Nothing much was meant to change. Okay, it's just a bit of history lesson about New Zealand curriculum. Over time, there was a subject, once upon a time, called mathematics. 2009, it changed to mathematics and statistics. Is that not amazing? What's in a name? Well, I reckon planning. For one thing, you can get around these problems. And there's another thing, too. Statistics, as sure is in there somewhere down the bottom. Okay. So this is what's going on all levels from K to 12 in New Zealand curriculum that's coming through. There's 3 strands going through all years. One on statistical investigation, which is skills and habits for doing. One on statistical literacy, which is the same sort of thing for interpreting, critiquing work done by others. And another strand on probability and mathematical type connections. The investigation and literacy strands are anchored to the investigative cycle, and we've got that poster in big A1, sort of this size, on almost every classroom wall in the country. What else did I want to say about that? Can't remember. Anyway, we've got, this is a quick diagram. What I want you to have a look at is the little discs labelled S. And that gives you an indication going through time of market share. It's to be compared with number and algebra and geometry and measurement. And you see we've got a pretty good presence increasing over the school years. I want to contrast a little bit about New Zealand and the US. New Zealand is a small country, not many people involved in the decision-making loops, so we're pretty flexible, we can sort of spin on a dime. The US is like this giant ocean-going aircraft carrier, very, very hard to turn around, but it's got a large, eager and enthusiastic crew. If you look back in our boat, we've got about 4 people, and that's about right. But we're still trying to change the world, but we're held back by only 3 minor problems. Now, there's some dangers of moving too fast in rapid, underfunded, top-down process. You have to make decisions before you go to explore their consequences. And probably we've been a bit overly ambitious, prescribing things we're not entirely sure on how to deliver from. But otherwise, the alternative is to wait 18 years, right? So one big hole was inference, so that's where our story's going. Now, doing statistics without making inferences is boring and largely meaningless. In New Zealand, our pre-grade 12 students have been encouraged to make inferences about their data for years, without any scaffolding or rational basis on which to make them. It wasn't built off sampling variation. And we wrote into the new curriculum that people should be doing 3 years of informal inference from ages 14 to 16. Good stuff. then, oops, we don't really know, and I don't think anybody else does, how to do this system-wide, so that using average everyday teachers to average everyday students across a whole system. So that was a bit of an oops. But there are some benefits of panic. When you take panic and combine it with guilt, it's pretty good for spurring action. Well, at least it works on me. And also, trying to do inference at a stage too young for the usual machinery sort of frees up your thinking. You can't do it all the ways you're used to thinking, so you have to think of new ways. So that's been a benefit, I guess. It's really an enforced case of letting go to grow. So, statistical inference, what is it? Well, how am I using the words, in other words? I'm using the standard statistical usage. I'm using it as the stuff of confidence intervals, p-values, posteriors, all that sort of stuff. And what's that all dealing with? It's just ways for accounting for uncertainty. But not any old uncertainty. It's a particular sort of uncertainty. It's the uncertainty due to sampling or randomising. Okay, in well-designed and executed studies. It's a very narrow area and a small part of the whole statistical enterprise, right? We're sort of focusing in finally on some little bit there and under my magnifying glass. Okay, somewhere in the middle of the analysis cycle. And we don't want to stay focused there all the time, but that's what we're going to do today. We've got some parallel work focused on telling data stories, which is holistic type stuff. So our plan of attack for this was basically to try to identify and work from a minimal set of the biggest ideas of statistical inference. Why? Why a minimal set? Basically because, as we know, students can't pay attention to too many issues simultaneously. So we want to make those few connections that matter most. That's the wish list, if you like. We want to eliminate busy work. We want to put an approximate big picture securely in place, and then over a period of years iteratively refine the details, add subtleties and make corrections. And we want to exploit the power of the visual sense. Okay, we also want to integrate it within the cycle. Okay, now building inferential ideas takes time, but what we want to end up with at the end of that time is an implementation in which the equivalent of a statistical significance decision can be made extremely quickly. In the context of a particular investigation, the mechanics of the inferential step should not be at all demanding. That's the sort of the goal we're setting ourselves, and why about that? Well, whenever students have to struggle with implementation details, the big picture gets lost. So I've got a quote here from George, and we all know that George is a very wise man. And so let's see what he has to say. Now, I've lifted it a wee bit out of context, but it works really, really well. Notice how the more attention you pay to any one element, picture, story, theory or rules, the less attention goes to the other three. In the step, whatever it was, you have to, whatever it was. And the more effectively you do that, the more the story fades into the background. Okay, I think there's a lot of wisdom in that. So whenever students have to struggle with implementation details, you lose the big picture, including any consciousness of why you're doing what you're doing and what it all means when you're finished. So we were thinking that ideally we wanted students to, among other experiences they have, to be able to have experiences where they can go around this cycle. They can ask a question, get the data, obtain the graphs, make descriptive comments, inferential conjectures, maybe make something like the call on a direction of group differences, and write up the whole story, all within a 1 hour lesson period. And if they could do it twice, that would be even better. Okay. And we also want that inference step to be able to be made, if we can, without them taking their eyes off the graphs. So that all the information's in one place, basically. Okay, now what am I saying here? It's all about this. You can see these sort of woeful-looking individuals, separated by high mountains. Very, very lonely. What we're trying to facilitate is this. What we're trying to do is remove the barriers to making connections. we'll go back to that. So we've got all this stuff that I've been through already. We should also try and end up with things that have connections to the more formal methods to be used later. We're after something like a developmental pathway. And here's our recipe. Blend hands-on activities and novel computer animations. Add the spirit of John's Chooky and stir. And then bake, but don't half-bake. Now, statistical inference, as I said, is a response to what? It's a response to that particular type of uncertainty that is caused by having data from random samples rather than the whole universe. That's the nature of the beast. It has nothing to say about design, execution issues, data quality, data relevance, importance. There's a whole lot of other really important things that it has nothing to say about. The other big thing in this picture is sampling variation, which is, in a sense, is a bit of a misnomer. It's basically, we used to also talk about sampling error, and it's, if you put those two ideas together, you're getting more or less what we need. It's really, we use this expression as a code for the set of ideas and experiences motivating the need for inference, and also suggesting how we do it. Not just how samples differ from one another is what the words suggest, but also how they relate to the parent population process distributions or whatever else they're coming from. So that is the nature of the problem and some pointers to solutions. So the corollary to that, as I said, is that we should initially approach inference by exploring the nature of sampling variation. Okay, there's not anything too radical there, except sampling variation is difficult, students just don't get it. Well, I'm saying maybe that's a consequence of how we go about it. Okay? Maybe there's stuff here that we can let go to grow. So what we're trying to do is take a very small set of ideas, run as far as we can with them, and I think you'll find that that's quite a long way. Our goals are more satisfying and rational ways for beginners to answer interesting real-world questions, and also to build important intuitions to base future learning on. It's about intuition. So what are we going to let go to grow? That's some of the things we're going to let go. Calculations, theoretical distributions, null hypotheses, and conventional representations of sampling variation. How are we going to let theoretical distributions go? We're going to build inferential ideas in terms of sampling from large finite populations. In particular, because the way that we've been thinking of this is for the school level, the particular population, we're going to be using the databases at Census School New Zealand. Large quantities on data of large quantities of kids. And we're going to treat those as populations to sample from. And even though we develop the ideas in this context, we'll actually apply them more generally. What about letting null hypotheses go? Why do we want to do that? No one actually believes, you scratch any statistician, nobody actually believes their null hypotheses. They make no sense at all with population data. They're basically an artificial device that lets us do some probability calculations and get some sort of uncertainty measures. Now, students actually find it very hard to think this way. What would the world look like if there was no effect, instead of the way it really looks now? I think this is a little bit like trying to look at the world while standing on your head. Now, why would anyone want to do anything quite that unnatural? Well, basically, we want to postpone doing unnatural things like that as long as possible. It also causes the silly mistakes, the no difference, misconception. What we're going to do is replace the sort of no difference idea by when you look at something like that, we want to be able to make a call on the direction of the effect. Yes, A looks bigger than B, or I can't tell. In other words, A's tend to be bigger than B's back in the populations they came for, versus I can't tell which is bigger. If I looked at it again, it could easily turn out the other way round. No idea there about these things could be the same. They almost never are the same. Now, I also want to let go conventional representations of sampling variation. Well, there's a couple of sort of combination dot plots, box plots, which I quite like to use. And let's think about now, how do we usually learn about sampling variation? Well, it goes a little bit like this. Or at least it would when I think things. Okay, we look at that and then we run off somewhere else. And somewhere deep under the earth, there's an ancient alchemist in a cave. That's us, folks, when we're in our classrooms and offices. And they conjure up wondrous visions. Now, I apologise if that's your applet, but it came up first on Google Images. So you're doing really well. And then somehow, we run back out. And there in the clear light of day, we have to try and, bring back to mind this vision of what happened back in the cave in a totally different dimension, and not a parallel universe, in a totally different universe, and make a meaningful connection between that picture and that picture. And I think it's not surprising that those connections often fail to be made and these things just fade away. So we're going to try and let that go to grow. Now, what's Hamlet doing here? And William Shakespeare? Well, inside Hamlet, there's another play. The play within the play. Okay. And inside this talk, there's another talk. The talk within the talk. And what I'm trying to do here is now start playing a talk that I have with teachers. Now, with the movie within the movie, it's always a bit, confusing about, am I watching the movie or am I watching the movie within the movie? And so is this the talk or is this the talk within the talk? Well, hopefully you'll be able to figure it out. Okay, so one of the things I want you to do is basically just try and let go of all the statistics, let it all melt away from you. I know that sounds a bit zen, but I want you to sort of, come to this childlike and experience all anew. So I want you then to step into my world. So we're going to start by looking at some data, and we're going to get it from Census at School New Zealand. And I'm going to look at one simple little categorical variable, which is, how did these kids get to school? And I've taken a sample of size 100. It's the sort of thing you do when you're in statistics, isn't it? And I've had a look at how kids go to school. Now, there's a sort of a myth that kids don't walk to school anymore. They all get taken in cars and SUVs and dropped at the school gates. That's obviously false, isn't it? The walking is still the biggest group. Okay, so I'm going to look at it again. Here's another sample of 100 kids. It's changed a little bit. The cars come up a bit. The walkers have dropped off a bit. I'll look at it again. Now, where have all the walkers gone? Hardly any. The car is king. Okay, I'm getting a different picture from each of those pictures. Teachers often find that surprising. I'm now going to look at something, the heights of boys and girls aged 12. Why would you ever do that? Well, actually, there's a bit of a folklore that there's a stage of development where girls mature earlier than boys and they get taller. And that probably happens about 12, so we'll go and have a look at that. So I've taken a sample of size 13, and yes, girls bigger than the boys. Well, you've got the picture now, haven't you? The game I'm playing. Look at it again. Yes, they're bigger than the boys. Look at it again. Oh, now the boys are bigger than the girls. These things obviously can't both be right. It still starts to worry you about sampling, doesn't it? If you look back in the database, I've got something like 5,000 boys, 5,000 girls at that age, and yes, there's a 1 centimetre difference in it. Okay, I'm going to look at something different now. This is a teaching activity on the Census at School site. It was built in about 2005, 2006, around the sort of Da Vinci Code idea, and it's just looking at, basically it's just looking at heights versus arm spans. So I've had a look at that, taking a sample of size 200, and you can see it looks a bit like you might expect. We'd expect a linear pattern, wouldn't we, with these dimensions? Something a bit funny with some sort of dribbly stuff going on below. Look at it again. Look at it again. Look at it again. Put them all together. Okay. So we're getting the same basic idea of a sort of like aeroplane fuselage shape. And then we're getting things that look like bits falling off this fuselage. With all the flying I'm doing lately, that's kind of scary. Now we'll go back and have a look at them all. So there's 30,000 kids. And what do we see there when we look at 30,000 kids? Well, we see, oops, come back. We see this big sort of cigarette shape. Let me do it here. We see this big cigarette shape here. It's the sort of thing we'd expect. That's the primary feature. The secondary feature is another blob down here. Any ideas what that secondary feature is? We're doing arm spans versus heights. They're meant to be doing this, right? There's a whole bunch of them are doing this, even though they've been told very carefully to do this. There are other detailed features. What other detailed features can you see in there? We can see some heavy rounding around the metre, the 1 metre thing going vertically, and other little bits of rounding going in. There's some stratification going in there. Okay, so there's all sorts of stuff we can see in there if we look at the whole picture. So, remember I'm still talking to teachers. We're talking now about description versus inference. Description is a very, very important thing, even if we're mainly interested in inference, because that's how we start to make sure that students actually, well, educate their eyes, start seeing what they're meant to be seeing, and knowing they're actually seeing it. But also being able to describe, what's happening to these people at this time, in this place, right now. So description is what I see in the data in hand. Now description has a theme tune. But of course we're usually not interested in just a narrow number of people who are at a particular point in time and so on. What we're wanting to do is to make inferences back to a wider reality, back to the populations or wherever these data came from. And inference also has a theme tune. Now, I thought we had a natural propensity to move early to inference, except when I asked my question at the beginning of the thing, and nobody was interpreting those questions inferentially. I thought everyone would. Anyway, nothing like a theory biting the dust. Now, many people, I think, many of us, including me, are a little bit I think there's something that happens when statisticians talk about data. We tend to drift between description and inference seamlessly without really signalling what we're doing. I mean, we move naturally between these worlds. But I think when we do it, it's very confusing for beginners. So I think that's something to pay attention to. Where else am I going with this? Still back in the talk within the talk, I remind you. That's what these little things up in the corner mean. So often we're coming to believe that something that we see in this data is a reflection of something that's occurring back in its parent populations. But we always know that what we see is at best an imperfect reflection of the way it really is back in those populations. So I think it's a little bit like this. Looking at the world using data is a little bit like looking through a window with ripples in the glass. I pulled this off a mad glass manufacturer's website. You get the point. Okay. We'll put it this way. That's the better one. Looking at the world using data is like looking through a window with ripples in the glass. What I see is not quite the way it really is. Go back there. There's the world. Here's what I see through my Ripley glass. What can I make out? I can approximately make out the big features, which is basically the aircraft fuselage. And I'm getting a pretty good rough impression of that every time I look. I'm not really seeing any of the other features. I'm getting some slight hints of the stuff down at the bottom, but not enough to really resolve it. I can't see any of these things about the roundings. No, all that detail is lost. I'm only being able to see the big, big features. So that's my metaphor to set the stage for statistical inference. What I see is not quite the way it really is. We've got patterns in populations. They get distorted by sampling variation. It gives us the patterns of what we see when we look at our data. The variation we see in data is a combination of real variation, differences between people, and then other induced things. And here we're just focusing on sampling variation. Okay, I've just turned that around now, going from populations to data. And then we've got the idea of what happens with small samples. Well, that's like a very, very Ripley window, isn't it? You can sometimes get quite big distortions. Big samples is like a window without many distortions in it. The worst we get is small distortions. Now, it's a bit of a no-brainer, really, isn't it? Bigger sample size, more information, lets me see more clearly what's happening back in populations. So we're going to look now at some sampling variation. So go first to how did they travel to school? And I'm going to come and have a look at, what will I have a look at? I'll look at samples of size 300. So, there's my first sample of size 300. Okay. Now, what happens when I sort of pluck it and do it again? See what's happened? Where the old bars were, they've left a little memory in blue. They've left a footprint. Do it again, I leave another footprint. Just focus on one bar till you see it happening. This is sampling variation for category data. Now, that's got, those pictures have got transparency for overprinting, which slows them down. So I'm going to look at sort of samples of size 50 now with the earlier, more primitive version of this. Well, let's play that one. See, I want to do that, I want to do that. Back to here. Okay, so there's that same thing played out with different sample sizes, 1,000, 300, 100, 30. Same big picture, look at samples of size 1,000, big samples, the worst we're getting is small distortions. Samples of size 30, we're often getting very big distortions, very big discrepancies between what we see and the reality. What can we learn from populations taken from samples of size 30? Classroom size samples. People do it all the time, right? Very little. The information content of category data points is very small. You need very large samples before you can say anything particularly useful about it. And actually that's a big surprise to teachers. It's an unfortunate fact of life. Things can be a bit better with measurement data. So I'm going to go next to some measurement data. And first I will play something about resampling with sampling from a population. This is looking in census at school. It's looking at the actual histograms of girls' heights aged 13 and 14. Okay. Unfortunately, we don't see that, so I grey it out. It's faded into the background. That's what we don't see. Then I'm going to take my first sample. And guess what happened the first time up? We know what the story is here. 13-year-olds and 14-year-olds. First time up, my 13-year-olds are bigger. But that's not really why I wanted to do this. What I wanted to see, what does repeated sampling look like? Well, it sort of looks like that. There's a lot of things you can see going on there. You can see what's happening to the spreads, you can see what's happening to the whiskers, you can see what's happening to the centres. There's a lot to be going on. But it is showing you what is happening to the picture that I actually look at as you do repeated sampling. Now, that's not too bad. I'll play an older version that plays slightly faster. You can there's some sort of retinal memory that can go on if you do something like that very, very fast. But it's not really leaving you with any record of what's going on. I'll do one more of these same sorts of things with sample size. Okay, I'm going to take samples of various sizes, 20, 100, 500. And I'm just going to do it over and over again. And I started doing histograms at the bottom because they draw faster. You can see quite a lot in terms of the relative movement there by sample size, but we're going to have better ways of looking at these things. And as I was saying, what's really not so good about that is it's giving you no sort of permanent record of the variation. So the next idea I came up with was this. And it's the same thing as we've had before. We start with saying, I never do box plots on their own because they're such abstract things. I just use them as a summary of the dot plot. So here's a few of them to get you started. Then we're going to switch to box plots. And we're going to play the same game we played last time. And I take a new sample. I'm going to leave a record of where the old one was. So the medians are going to track in blue and the rest of the box is going to track in red. So you watch where that box is and you should see red and blue lines appear. Okay? And let's play that a wee bit faster. Okay. I'll do a two-sample version, I guess. Will I? I'll do an old two-sample version where things play fast. So what are we getting out of this? That's what we're getting out of this. We're getting a dynamic impression of sampling variation in the same space as the graphs that we actually look at. I don't want to do any more of that now. But then you start thinking about this and you contrast what's happening on the left with the alchemist in the cave. I think it's a no-brainer. My wife tells me the other one's much more interesting. But anyway, what's the effective sample size look like here? Oops. Oh, there it is. It's pretty obvious, isn't it? Okay, but the problem with all this, it's all stuff happening on a computer screen, right? And so we've got to ensure that the students don't see this. It's just computer magic. We've got to somehow anchor what's happening on the screen to things that are real and touchable, and etc. And some of my colleagues have got some real good ideas about how to go about doing this, Maxine and Pip Arnold in particular, and I'm going to steal from their ideas for my breakout this afternoon. So what I'm trying to do here is to plant a reflex that goes of the form this. Whenever I see something that looks like that, what I'm going to remember in my back of my mind is this. Mine could be like that on the left side of reality, on the right side of reality. And somehow I've got to take this uncertainty about where the real boxes are when I make my comparisons. Go back to our data. Should I say that girls are taller than boys? Dare I make that claim? Back in the populations, actually one of the other things we believe is hitting the same phrases over and over again to try and burn them into the brain. Now my boxes aren't quite in the right places. I can only say which is bigger if the extent of shift that I see overpowers my uncertainty about where the boxes should be. And there's the effect of sample size again. That's something else to be in the mind. The level of uncertainty, and I think it's graphically obvious there, the level of uncertainty depends on sample size. So we've got this sort of schematic here. This is part of a handout we've prepared for teachers. And basically what's happening there is an increasing shift as you go from bottom to top. And at the top, I think nobody's ever going to have any difficulty with saying, yes, B is bigger than A. All right? And actually, if you play these games with samples from about 20 up, even down to overlaps like this, you can just call it straight off, not do anything at all. At the other end, down here we're obviously in don't tell territory, and up here there's a transition going on. And we know the amount of separation we have to see, the amount of shift we have to see, depends on sample size because of what we saw in those previous pictures. I'll just jump over that. Just again from a teacher handout, just to emphasise a couple of things, is that we're telling them to emphasise the visual, keep the eyes constantly on the plot. Also trying to tell them this is only one small thing in the statistics curriculum. This isn't the whole thing. This isn't the be all and end all. This isn't the meaning of life. There's also some sort of technical notes about these things. Now, how to make the call? We've come up with some different possible reasons for saying when is the shift big enough, which we hope is sort of age level specific. Now the first thing that we came up for is trying it at about age 17 is something we called the 3/4 half rule. And it was derived by things that are naturally going on in the classroom from some of the research that Maxine and others have been doing. The kids tend to compare features vertically. They tend to like to see things like, oh well, this box is all to the right of that median, things like that. So we'll leverage that to make a shift measure. And that's the one that we are using that way. There's a little bit of technical stuff down there. It works pretty well, quite close to nominal levels for samples about size 40. And this very first level, we're not playing with sample size. We're just using classroom size samples. And the reason for that is people tell me that they're not very good at actually seeing groups as entities. They're not actually very good at seeing shift. So part of what's going on here is to try and get them to see shift. We've had this sort of little bit of intuition of this, the idea that the majority of one sample is to the right of the great whack of the other sample. And the great whack is becoming famous now, and it was invented by Matt, who's here. Okay, now young children don't see aggregates and shifts, and I was sort of dreaming about this recently, and I was to come out again with a metaphor, as I sort of like to do, that might help a little bit, and I came up with this one. And maybe something like this would be slightly more memorable. Well, that's enough silliness for now. We've still got to bring this in somehow. Level of uncertainty depends on sample size. Well, now appealing to teachers to things that some of them know, or sort of know. What does the two-sample t-test do? What it does is it looks at the difference between centres and compares that to an average measure of spread downweighted by square root sample size, doesn't it? Or another way of thinking of it looks at the distance between centres as a proportion of within sample spread, with cut-off that depends on sample sizes. So we're going to sort of try and go off in that direction. Bigger cut-off values, smaller samples. And I should show you that everything that we're doing works really well for normal chi-squared 4, which is pretty darn skewed, T4, which is fairly heavy-tailed distributions. And here's what we're trying for the next thing, which we try to look at a difference in centres and compare that to spreads. Entirely visually. Now I did a bunch of playing. Well, first I wanted to compare distance between medians to the sum of box widths, because that was sort of more like the t-test. But they told me too hard, they can't do that. Look at that. And actually this works pretty well. And I've done a whole bunch of simulations and come up with some nice simple round figure rules. If you look at the distance between medians and compare it to this overall visual spread here, if you're looking at samples of about 30 and you call that shifted far enough if the difference between medians is basically bigger than a third of what I can see, that works pretty well. If you go to samples of about 100, if it's bigger than about a fifth of what I can see, that works pretty well. And if you want to go further to 1,000, you can use a tenth. Now there's a little bit of trade-off there between sort of error rates and nice round numbers. Want something memorable and easy. And also, basically, want to stress eyeball judgments. Just look at it, make a quick eyeball judgment. That's all we want. Then we're going on again to another level. And actually, I'll go back to that. Actually, those things aren't too bad messages to take away for ourselves if we want to just look at something and we've got no information. It's not going to lead you too far astray. Now we're getting into another set of information which comes more quickly, more directly from the picture that we're seeing. It's all hinging off the picture. I got this. Somewhere down there's an unseen population, and I know that this sort of thing is happening. Okay. So, I know that the actual sample medians are bouncing around the truth, and that I can sort of make some sort of visual comparison and say that the data median is seldom further from the truth than this. Now I'm going to do the standard sort of thing we actually do in statistics, but I'm just going to leverage the language, which is another expression of maths, and turn this around. The truth is seldom further from my data median than this. So I want to put on some sort of uncertainty interval around what I see. Slight problem though, as you all know. I don't actually see the width of this uncertainty interval because I only get to see one frame of that moving. So we need some sort of estimate of the width of this uncertainty band. Now all the other rules, there are ways I can see to sort of, for people to discover something similar to the rules rather than just tell them. But this one I don't know how. Well, we know the uncertainty band should be wider for small samples and so on. And I've just, jumped to the answer. Now what is the answer here? I've done it in formula form, but basically it's 1.5 box widths over square root sample size. Draw that on as your uncertainty interval. It's actually a pretty good 90% confidence interval. Okay, now what are we going to do with this? When we do a comparison, we'll just appeal to the intuition that says, for the group A, I reckon that the truth is somewhere in there. For group B, I reckon the truth is somewhere in there. If the plausible values for A are separated from the plausible values for B, then I'm going to say B is bigger. Fairly intuitive, fairly simple to operate. Does anyone know what I've got here? I've drawn them slightly differently. Do you know what I've got here? I've got a very slight simplification of Tukey's notch box plot. I put the little intervals on there because I think it visually gives the uncertainty interval idea better. And actually you can go better than that. You can't use that just to read off something like significance. You can actually read off a confidence interval for the difference. There's the biggest the A value is likely to be, the smallest the B value is likely to be. So there is a lower limit for the difference. Go to the other end, there is an upper limit for the difference. So I can actually eyeball that graph and read off a confidence interval for the difference. Okay, so putting it together, and there's not a heck of a lot of it. I see that. Hopefully I remember this. My boxes aren't quite in the right place. Hopefully that reminds me that I need some uncertainty intervals. And when I'm there, I'm basically done. From those intervals, I can read things like group directions of effects. I can read off confidence intervals for differences. Now, of course, there are embellishments, lots of other things we can do. But, if we failed on everything else and could just deliver those 4 little steps, we wouldn't be doing half bad. They're practically useful tools, and they're simple versions of bigger ideas of inference to build on. One embellishment, of course, is the sample size effect idea. Okay. Now, this is just the data viewer at Census School New Zealand. One of the sorts of graphs that it delivers. This basically is set up for sampling and then displaying data in a way that lets you go through that cycle very quickly, because you don't have to make lots of decisions. Okay? And if you click a particular age-specific box, you get those sort of like little uncertainty intervals stuck in on there. Okay, now we can carry this same idea over to category data. So here is my initial bar graph, to which I have to try and bring to mind that. So what do I need? I need some sort of uncertainty interval. Well, I'm never going to know how to put these ones on, right? This is kind of complicated. If you want to make good approximations here, you have to be able to take into account correlations and all sorts of things. You have to think pretty hard to put those guys on. But anyway, once they're on, we're back to where we were. It's trivial. You can read off significance type things about differences. You can see confidence limits on the sizes of the differences. You can play the same game with 2 variables. Same idea. I've broken out the walking to school distribution by 2 cities where kids live. And I can look for differences between cities, and the differences I see are between bikers, lots more bikers in Christchurch, which is a flat city, versus Auckland, which is a hilly city, and the walkers going the other way around. Now, there's a lot of talk in ASCOTS recently about randomisation tests. How does random assignment animate? Well, I'm going to have a look at that now. I'm going to play the same sorts of games that we've been playing before. Now, I warn you, I haven't done the memory version of that. I've just done the sort of straight vanilla one, which I finished off doing just last night. Okay, so there is 60 observations spread out on something. It's just a random sample from a normal. Actually, what I'm going to do... Now, if you're going to make this meaningful, you're going to have to sort of wheel in a bit of H0 here somewhere, I guess. But anyway, that's what I want to look at. I just want to have a look at the effect of pure random assignment and nothing else. So I'm going to randomly colour half of those circles red and the other half blue, and make them into 2 groups, and then do a plot of the data. So there they are, randomly recoloured. Take them up there. And I've actually left ghosts of what they were before in the middle, because that's going to be useful later on. And then when I get to the top, there I do my graphs. Okay, so that's my first random assignment. Here's my second one. This gets a bit annoying, okay? So I stop doing it. Just do it a bit at the beginning to get the idea. And what does random assignment look like? It actually looks a heck of a lot like random sampling, but we shouldn't actually be too surprised by that. Okay, so there's random assignment. There's a little animated GIF. Okay, in summary, and we're still within the talk, but this is the summary of the talk within the talk, and it's also the summary of the talk. Looking at the world using data is like looking through a window with ripples in the glass. What I see is not quite the way it really is. Description is what I see in the data in hand. Inference is what I think is likely to be happening back in the populations the data came from. In this talk we've concentrated on inference. Sampling variation alone can produce shifts in our box plots. Small shifts with big samples, big shifts with small samples. Makes no sense to read meaning into shifts in data of a size often produced by sampling variation. We've got some rules where we've developed some for kids for signaling when a shift is big enough that we can make a call on what group gives bigger values. I want to plant this reflex that says whenever I see a box plot, this comes to mind. Okay, we've got to take this into account. Does the shift we see look bigger than sampling variation would produce? And, well, you can read that stuff. That's putting it all together. What I see, what I remember, but that tells me I need uncertainty intervals, and just the shimmering gives you those uncertainty intervals, I think. And once I've got them, I can read off which is bigger or can't tell, and I can read off confidence limits for the difference. What do we do if the shift isn't big enough? Then we can't make a call about who's bigger back in the populations. We simply don't have enough information. When does that happen? Well, it happens frequently if the sample sizes are small. We know that. Going back to my metaphor, that means very little data, a very Ripley window. Okay. It's hard to see things through a very Ripley window. It happens when the differences between the populations are small. What does that correspond to? That corresponds to looking for fine details rather than gross discrepancies. And we know we can't see fine details through a Ripley window. I guess those are subjects for another talk. And that's it.